Thanks for joining us on our second lesson of electromagnetism. We'll be looking at part 2 of our magnetic field lines as well as overhead cables. Now we'll start off by looking at the magnetic field lines produced in a solenoid when current runs through it. Now a solenoid is basically pieces of wire that has been coiled up around in a circular form, just pretty much as indicated here in your sketch. Now the current will be running then through these loops of wires to the other side, always still conventional flow, which means from positive towards negative. And so it will continue flowing until it then reaches the negative part on the other side. But seeing that these loops are then all connected in one, the current will be flowing through them in the same direction, either everything pointing upwards or the current will everything be pointing downwards, just depending on whether your positive or negative lies on which side. Now what is all unique about a solenoid is when we're going to create a magnetic field, it's not just going to be a circular magnetic field like we've seen in our straight current carrying conductors and our loop of wire. Here we're going to actually form a bar magnet on the inside of the coil. Now note though that this bar magnet is imaginary, but it will basically take up its specific north and south as indicated by making use of our right-hand rule within this coil. So we're going to have a magnetic field that will be produced when current runs through the coils, but this magnetic field, which is imaginary, is going to act like an imaginary bar magnet. Now, in order to indicate the direction of this bar magnet, we'll be making use of our right-hand rule. But the right-hand rule is going to be slightly different than the one we've used in our straight current carrying conductors as well as in the loop of wire. Now, we are going to be making use of our thumb not to indicate the direction of the conventional current, but to indicate the direction of the magnetic field. And our fingers, our four fingers that will now cool, they will now cool in the direction of the conventional current. Now if we've got our positive as connected here on the left hand side, it means that the current will be flowing as indicated. So let's go and take a look here at the middle part of where my solenoid actually lies. So take your four fingers that will now cool and cool them then in the direction, in this case upwards over these coils. Then you would note that your thumb is now in this case pointing towards the left hand side. Now your thumb's tip of it will indicate the north, and then the remaining part will then indicate towards the south. So if my thumb is then pointing towards the left, it means this imaginary bar magnet that now formed inside our coil will have its north to the left hand side and the south towards the right hand side. Now we do know that there is a specific direction for our magnetic field lines in a bar magnet like you've done in grade 10. Those magnetic field lines always goes from north towards south, and you would also take a note though that there will be magnetic field lines pointing out and into the north and south, making sure it's out of north and into south. Now let's just quickly go and draw these magnetic field lines a bit better so that you can see them. So for our bar magnet, as said, it goes from north towards south, but because this is an imaginary bar magnet that doesn't actually exist, it means that these magnetic field lines will now be continuous within this coil. So these magnetic field lines will actually meet up again from their beginning and starting points as indicated. Now that means our magnetic field within this bar magnet is going to be going from south towards north. But outside of the magnet it goes from north to south, but on the inside it goes from south to north. Now if you should go and take a top view from this solenoid, you would note that as you view from the top, you'll only see these cooled parts coming up as they make our loops. Now we would note that in some part these coils are coming basically towards you, and then they will bend to go back into the paper. So we're going to be making use of our dots and our crosses to indicate this. Coming towards you means a dot, going into the paper means a cross. So we can go make use of our dots and crosses as well to indicate our magnetic field lines. So here's our solenoid. The dots means that this loop is actually coming out of the paper and back going into the paper where we've got the cross. Now each one of them will obviously have their own little magnetic field line towards them, and they would then be pointing all in the same direction in a specific row. So let's just quickly go and take a look. If I have my dots, their thumb must be pointing out of the piece of paper, and that means the fingers are going to be curling anti-clockwise. Now I'm only going to be doing just the first and the last one so you can see the overall effect. And if we look at our crosses, that means it's going to go in a clockwise direction as your thumb points towards the piece of paper or the screen in this case. Now what's important is we know that there's going to be magnetic field lines that is going across and around these specific loops because of the fact that there's going to be imaginary north and south forming inside of this solenoid. But you can then also see the direction as it is then formed on the outside parts here with your magnetic field lines. This shows that it's coming in towards. So here my magnetic field lines is going in, and then you'll see that it's going out. And that's all indicated by the specific indication of a magnetic field lines here. Field lines coming in, travels through to the other side, and over here it means it's going to be going out again. So because of these smaller magnetic field lines that add up, they then create the direction of our bar magnet, which is then going from, in this case, south to north when inside the magnet, but on the outside of the magnet, it goes from north towards south. Now what we can go and do is to go and place an actual piece of metal inside of this coil. Noting that there will be this imaginary bar magnet forming, it will then magnetize this piece of iron so that it will then end up having its north pole on this side and its south pole on the other side. So putting them inside of the solenoid, letting the current run through the coils will then induce the magnetic field onto this piece of magnetized metal and then making it a magnet for a period of time as the current is running through the coil. Now we would call this an electromagnet, seeing that it will only be a magnet as long as the current is running through the coils. Now let's go and take a look at a few properties of this electromagnet. So the strength of this electromagnet is dependent on the number of turnings on the solenoid. So the more pieces of wire is coiled around, then the greater the strength of the electromagnet. Secondly, the current running through the solenoid, that means the current running through our piece of wire, the greater the current, the greater the strength of this electromagnet. And lastly, the type of substance from which this metal is made. Now you do get again soft and hard magnetic materials, and we've discussed them in grade 10 where we said those ones that are easily magnetized is known as soft magnets. They lose their magnetism though quite quickly. But if you've got your hard magnetic materials, they are though just referred to substances that can take a bit longer to get magnetized, but they will then have and keep their magnetism a bit longer. Now seeing that you will then induce a magnetic field if there's current running through a conductor, your next question might be, but what about all our overhead power cables? We transport our electricity from our substations to our homes and as well from the generator of electricity to the substations via these overhead cable lines. So that means that there is current running through the cables, and that also means there will be a magnetic field that will be produced around these cables. Now, many questions has arisen in the past whether that actually has an influence on the health of animals and people and even to crop or any plant material in the vicinity of these overhead cables. Now to date there has not been any scientific link to cancer forming and being in the vicinity or living in the vicinity of overhead cables, or even leukemia in smaller children, although some tests are still being done. They've also found that there's no link between the production of animals as well as the production of milk in cows or even in any of the plant produce if they are in the vicinity of these magnetic field lines. The problem just with placing our overhead cables underneath our ground is that it will still have a magnetic field surrounding it even if it's placed underground. We do know that having overhead cables has the risk of being stolen, as we've seen so many times before in our country, and that is then one disadvantage of having them as overhead cables across. Now the question which I would like you to go and attempt is to indicate the north and the south poles of this imaginary magnet that will form inside of the solenoid when current is running through the loops.